Okay, good afternoon, and welcome to class 13 of Physics 350, the Biot-Savart law, or as it's known in French, the Biot-Savart law, and this covers section 5.2 of the textbook. So we're really starting to get into magnetism now, and the Biot-Savart law is the equivalent for magnetism of Coulomb's law um, for electricity. Coulomb's law talks about what forces a, a single charge exerts on other charges, uh, and also what electric field is created by single charges. And the Biot-Savart law talks about the magnetic field created by little pieces of current. So we're going to be talking about, for now, steady currents, okay? So currents that run through wires that don't change their magnitude in time. And just to kind of get classifications clear, we've been talking about in previous lectures and videos, the case of stationary charges. And if we have stationary charges that aren't moving, that gives rise to constant electric fields, and that's the what we call the area or the regime of electrostatics. When we have steady currents, we imagine wires or a set of wires where we have currents whose magnitude don't change in time. The currents may wind around in space, and they don't have to be in one direction, but their magnitudes don't change in time. So that gives rise to constant magnetic fields, and that's what we call magnetostatics. So magnetostatics is the regime where to put it into mathematical terms, the charge density, rho, doesn't change in time because the charge in any particular position stays constant. And also, this object J, which is the current density vector, okay? It's basically the current per unit area, but it's a vector because current can go in any direction. So J is called the current density vector. And if that doesn't change in time, then we have steady currents and we get constant magnetic fields. Just as an aside, coming up in the course, if charges accelerate, so if we don't have stationary charges, if they start moving and accelerate, we actually see electromagnetic waves, which will be generated. So we'll see the creation of, by accelerated charges, magnetic fields, and then the magnetic fields then produce electric fields and so forth. So we'll talk about that in a couple weeks. If the currents change, so if we have a current and it changes, we get a changing magnetic flux in the loop that the current is a part of, and that changing magnetic flux turns out to induce a voltage around the loop that it's a part of, and that's a part of Faraday's law, which you may have heard of or you may remember, but which we'll be talking about also fairly soon. Anyway, for now, steady currents. So let's look at the magnetic field of a steady current. This setup it's a lot like the setup for Coulomb's law, except Coulomb's law, we had a charge and an observation point R, and then a separation vector between the location of the charge and the observation point, script R, and then we figured out the expression for the electric field at that observation point R. Here, magnetic fields are generated by moving charges, So currents. So here we have a loop of current, and we consider a small part of that loop, and that part of that loop is a little length, dl, or dl prime, since it's a source. We use prime for the source of the field, and it's directed. It's a vector, so dl prime is a vector, because the direction of the loop changes as we go around, and it turns out that the contribution of that little piece of current to the magnetic field at this point R depends on the direction of this current, because magnetism is a vector force. Okay, so the Biot-Savart law, or the Biot-Savart law, says, and we'll break this down in a minute, and do an example, that the magnetic field at this point R is equal to a constant, mu naught, which I'll talk about in a second, over 4 pi, times the integral, as we go around this loop, of the current cross product with the unit vector along the separation vector, script r, over the separation vector squared times dl prime. Okay, so since the current is constant, and we're talking about a steady current, we can pull that current out in front, and we get mu naught, this constant, over 4 pi times the steady current, times the integral of these directed length vectors, dl prime, cross with the, as we move around, the unit vector connecting, or move in the direction of the observation point. So from the each respective length of wire to the observation point. So here, the unit vector would point in this direction. Over here, the unit vector would point in this direction. Up here, the unit vector would point in this direction, and so forth, over r squared. So we can see a certain similarity to Coulomb's law, in that we have the field is proportional instead of to the charge, is to the current, and it is the contribution of an individual piece of current goes as 1 over r squared, just like the contribution of a charge to the electric field goes as 1 over r squared. So there's some similarity, but this is a little bit more complicated, because the magnetic force is a vector force, and the magnetic, as we saw last time, the Lorentz force is at right angles to both the velocity and the direction, the velocity and the the velocity and the magnetic field. Sorry. Okay. So so this is the expression, and we're going to illustrate that in a second for a particularly simple case of a long straight wire. Mu naught is called the permeability of free space. It shows up in the equations that we're building towards in this course, called Maxwell's equations. And for us, it's just an arbitrary constant. Well, not arbitrary, it has a value, but it's just a constant. And its value is 4 pi times 10 to the minus 7 Newton per amp squared. Okay. So with that, we can figure out or verify the units of magnetic field, because we have, let's see, the units of current are amps. Well, the units of the permeability are Newton per amp squared. We multiply by amps, we get newtons per amp. And then here we have units of meters in the numerator, this dl prime, units of meter squared in the denominator. So we have newtons per amp times meters over meter squared, or newtons per amp meter, newtons per ampere meter, and that's called a Tesla. Okay, so that's the units of magnetic field. Okay, so let's just do a sample calculation. The field of a long straight wire. Okay, so here's obviously, and we assume this is infinitely long. We can't draw that on the screen here, but here's a part of it. And we set up our variables here. The current is, as usual, is I, and we'd like to find the magnetic field at distance s from the long straight wire, which carries this steady current I. And okay, so using the Biot-Savart law, we break up the current into a lot of little pieces, dl prime, and each piece dl prime has a separation vector which points back script r, which points back to the location where we're trying to find the field P. The distance, as you said, is s from the wire to the point P. And so in the Biot-Savart law, if we look at it, we have the expression dl prime cross r hat. Okay, dl prime cross r hat. That's always the expression that's a little, the rest of them are scalars. That's the vector expression, which is the challenge to evaluate. So here dl prime cross r hat for this little vector here, dl prime, is going to point out of the page, okay? So I can't indicate this in this video, but if you use your right-hand rule, for example, if you put your thumb in the direction of dl prime here, and your outstretched fingers in the direction of r hat, which is the same as the direction of r here, then your palm will be facing out of the page. So that's the direction of the cross product. The magnitude is the magnitude of the cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. So that would be dl prime, the magnitude, times the magnitude of the unit vector r, which is 1, times the sine of the angle between them, which is we've called alpha here. Okay. And then just for convenience, in the integration, we're going to need to, as the Biot-Savart law shows, we're going to need to integrate over all of these little lengths, dl prime, to get the total magnetic field. We're going to relate this angle alpha, which is the angle between dl prime and r, to this angle theta, which is the angle between the vertical and the excuse me, the vector from P to the observation point P to the unit dl prime. Okay, so that turns out to be just dl prime cosine theta. So it turns out sine of alpha is equal to cosine of theta. So if you like, you can pause the video and take a couple minutes and try to convince yourself of that. So I'll let you do that now if you want. Okay, if you've tried it or you've already understood it, if not, I'll just summarize it briefly. And that is that if we draw a parallel line here, then the angle between this r separation r and this vertical line is this angle right here, this little angle right there between the vertical and this line is equal to 90, theta alpha, rather, minus 90 degrees. And the sine of alpha is equal to the cosine of alpha minus 90 degrees. Okay, so that's just a trig identity. And then this little angle here is the same as this angle here because they're both interior angles in this geometry here. Okay, anyway, so we have this written, the magnitude of dl cross r is written in terms of this angle here between the point P and our little length of current. Now we need a couple other relations before we apply the Biot-Savart law. So we're going to need to know the length dl prime. We're going to be integrating over theta, so we want to relate the dl prime to d theta. So to do that, we use trigonometry, and L prime is equal to S, the distance from the wire, times tangent of theta. Because if you remember, tangent of theta is the opposite over the adjacent. So this is L prime over S. So that means that L prime would be equal to S tan theta. Okay, so taking the derivative or the differential, dl prime is going to be equal to S times the derivative of tangent theta, which is 1 over cosine squared, that is secant squared, or 1 over cosine squared, d theta. And then it's also going to be helpful to express r, relate S and R, the separation S and R, when we use the Biot-Savart law. And the relation between those is the cosine, because the cosine of theta is equal to the adjacent over the hypotenuse. So that's just going to be S over R. Therefore, S is equal to R times the cosine of theta. And then not taking a derivative, but just manipulating that equation, if we take R over to the left side and S over to the right side in the denominator and then square them both, we get 1 over R squared. The separation squared is cosine squared theta over S squared. Okay, so now we've done the preliminaries, set up our angles. We've got our we've got all the ingredients we need to apply the Biot-Savart law. So here it is again. It's mu naught over 4 pi times the integral of I cross r hat dl prime over r squared. So, and here is, oops, come back. So we're going to use, as I said, as our integration variable, theta. So we're going to imagine integrating from a theta 1 to a theta 2 over all the little bits of wire segment between theta 1 and theta 2 to find the total contribution of the magnetic field to this point P from that wire segment. Okay, so we're going to integrate from theta 1 to theta 2 of 1 over r squared, which we determined up here is cosine squared theta over s squared, and then times dl prime, which is s over cosine squared theta times d theta. And then, and then the cross product brings in an extra factor of cosine theta, since dl cross r prime is dl prime times the dl prime here times cosine theta. Okay, so we can see some simplification happens. The cosine squared thetas cancel, and we have an s just left in the denominator. S over s squared is 1 over s. So we can bring, we're just left with a cosine theta in the integral. And we have mu naught I over 4 pi s times the integral from theta 1 to theta 2 of cosine theta d theta, which is mu naught I over 4 pi s. The integral of cosine, the antiderivative of cosine is sine. So we just evaluate that between theta 2 and theta 1, and we get sine of theta 2 minus theta 1. So the contribution to the magnetic field, the magnitude of the magnetic field at this point P above here, if the wire segment goes between angles theta 1 and theta 2, is given by mu naught I over 4 pi s sine theta 1 minus sine theta 2. Now, what happens if we want to take the whole long, or infinite, or a long, straight wire? Well, theta 1 will go to back the other direction to minus pi over 2. Theta 2 will go all the way to plus pi over 2. So theta 2 is plus pi over 2, which is sine of pi over 2 is 1. And theta 1 would be all the way back this way, so pointing back over here, which would be minus pi over 2, so that would be minus 1. So we get 1 minus minus 1, or 2. And so this is a factor of 2 for the infinite wire, and we just get that the magnitude of the infinite wire is mu naught I over 2 pi s. Okay, so and that kind of makes sense. The main point here has been to go through the derivation of and give a sample application to show how the Biot-Savart law works in this geometry. But if we take a look at the expression we get here at the end for the magnitude of the magnetic field, it's proportional to the current, which makes sense. If we double the current, we double the magnetic field. And it's inversely proportional to how far we are from the wire. So the further we are from the wire, the weaker the magnetic field gets. That is certainly plausible, that the magnetic field should weaken as we get further from the wire. Okay, what about the direction, right? This is a vector. This is a vector here. For that, we have to look at the direction of I cross r hat, or dl prime cross r hat. And above the wire, we said that dl prime cross r hat is going to point out of the page, okay, so, or out of the screen. So this is pointing towards you. The magnetic field would be pointing towards you at the point P. Down here below, if we did the same thing, then according to the right-hand rule, the magnetic field would point into the screen, okay? So in the region below the wire, B points into the page. In the region above the wire, it points out of the page. That gives us a right-hand rule, which says that if we put our thumb in the direction of I, that our curling fingers here will point in the direction of the magnetic field, because our curling fingers will point out of the page when they're above the wire, and when they go wrap around, wrap around and go down below the wire, they will be pointing into the page. So that's the right-hand rule for the magnetic field of a wire. And we can summarize that by saying that the magnetic field is equal to its magnitude, which is mu naught I over 2 pi s times phi hat. Okay, so if we take this as our z axis in cylindrical coordinates, then this that direction circulating around according to the right-hand rule would be phi hat. Okay, so we've used the Biot-Savart law to determine the magnetic field of a long straight wire, both its magnitude and its direction. In the next lecture, in next video, we're going to be using the Biot-Savart law to go back and look at the divergence and the curl of the magnetic field. Because we know the divergence and the curl of the electric field were very significant. We're going to be looking at that coming up soon. Okay, thanks for your attention, and see you in class.